Hello everyone, in this particular video we are going to talk about the oscillation, a type of oscillation, and the example that we are going to take is the spring mass system. Okay, we are going to derive the equation for the time period of the spring mass system. So for that we will just have a look at the video here, an animation, so which talks about and explains what is the spring mass system. So in this particular animation you can see that there is a block which is going to have certain mass and it is attached to the spring ring. Okay. Now this block will be oscillating back and forth. Okay. So that block is repeating its motion again and again after a regular fixed interval of time, which is called as the time period. And this repeating motion is called nothing but it is called as the oscillation. But we have a special type of oscillation which is called as the simple harmonic oscillation or a spring or a simple harmonic motion. Now this simple harmonic motion is a special type of oscillation. In fact, this spring mass system is also going to execute simple harmonic motion. Okay, so what is this simple harmonic motion? So in simple harmonic motion, the acceleration of the body oscillating is directly proportional to its displacement from the mean position. Okay, it is directly proportional. The acceleration is directly proportional to its displacement from the mean position. So here x is the displacement from the mean position and a is the acceleration. We try to understand that in the next slide here. Okay. So here in this particular diagram you can see that we have got a mass m, and this mass m is attached to the spring which will have a spring constant k. Now if I apply a force F on this mass, let us say I apply an external force F on this mass and pull it towards the right direction. Okay, I apply a force on it and I pull it towards the right direction. So when I pull it towards the right direction from within the spring, so you know that very well that the spring is going to get stretched. When I pull this mass, the spring will be stretched, and within the spring, from within the spring, there will be a force that will be coming into play. I'll call that force as the restoring force. So the force that will come into play here is called as the restoring force. Now, why this force that comes from within the spring, that arises into the spring, is called as the restoring force? That is because when you have pulled the mass by applying the external force F, the spring is trying to pull it back to its original position, x is equal to 0. Okay, it will try to pull it back to its original position, x is equal to 0, and that's why it is going to try to restore its original position. That's why it's called as the restoring force. But because of this force, the mass will come towards the mean position, but it will not stop there because it will have certain energy still present into it, and that's why it will move towards the left direction also to the same distance as it traveled towards the right, and that's how it is going to keep on oscillating, thereby executing a special type of motion which is called as the simple harmonic motion. So in this case, the acceleration will be directly proportional to the displacement from the mean position. Okay, this is called as the simple harmonic motion, where x is the displacement, how far you are taking the mass from the mean position. Okay, and a is the acceleration of the body. Now we will try to derive the expression for the time period. So now the force that came into play, which tried to restore the disturbed position of the mass F, that force can be given by Hooke's law as, by Hooke's law, that restoring force will be F is equal to minus kx. Okay, that restoring force is actually F is equal to minus kx, where x again is the same displacement from the mean position or equilibrium position, and k is the spring constant. What is k here? K is nothing but it is the spring constant. K is the spring constant. Now, what we will do is that we have this expression. Now, by Newton's second law of motion, by Newton's second law of motion, okay, we know that the force acting on any body is equal to mass of that body multiplied by acceleration. Okay, we know force is equal to mass into acceleration by the Newton's second law. So now we will put this equation 2 in equation 1, so that equation 1 becomes m into a is equal to minus kx. Okay, now here this m which is there, I will take it towards the right of the equation, and that will become minus k by capital M into x. Okay, now this acceleration, we know that it is nothing but it is the second derivative of position with respect to time, d2x by dt square. So I can write this as minus k by m into x. Alright, so now once we have this equation, I can write this k by m factor, this k by m, I can call that as the as some constant. We'll take that as some constant. Okay, so that k by m d2x by dt square will become minus omega square x. Okay, so here omega square is the constant that we have taken, and that is k by m. So omega from there would be equal to square root of k by m. That would be omega. Alright, and now here you can see that the acceleration is directly proportional to the displacement. Okay, we get the condition now. So once we get this condition that the acceleration of the body is directly proportional to its displacement from the mean position and directed towards the mean position, which is represented by the negative sign, we can say that this spring mass system executes simple harmonic motion. Okay, and thus we can find out the time period. So we know that the time period equation, time period is given by t is equal to 2 pi by omega. So we have got that omega here, that's the angular frequency, that will be 2 pi by square root of k by m, and thus this will imply here that t will be equal to 2 pi square root of m by k. Okay, now this is the expression for the time period that we have got. Alright everybody, so this is the expression for the time period of the spring mass system. So the motion will repeat itself after a fixed interval of time, and the time period will be directly depending on the square root of the mass and on the spring constant. Okay? This is the time period equation. That's it. Thank you.